Hello everyone. Today I will discuss Amdahl's law, which is an important concept in parallel computing. So in modern computing, we often use multiple processors to make programs run faster. But an important question is, how much faster can a program actually become? Amdahl's law help us calculate the speed up of a program when we use multiple processors. In this presentation, we will understand the idea of sequential versus parallel task, study the mathematical formula, perform a manual computation, analyze the limitations of parallel computing, and look at real-world applications. Imagine you have a big group project. One person writes the introduction, while the other 9 people work on the rest of the report at the same time. Now let me ask you something. If we add more people to the group, will the project always finish faster? Most people would say yes, but actually the answer is not always. And that is what Amdahl's law helps us understand. Before we talk about speed up, we first need to understand something called parallel computing. Parallel computing means doing many tasks at the same time instead of one by one. For example, imagine washing dishes. You could wash 10 plates one at a time, or you could have 5 people washing plates at the same time. Which is faster? Obviously the second one. Computers work the same way. Instead of using one processor, a computer can use many processors working together. But here's the important question. Does adding more processors always make the program faster? The answer is no, and that is exactly why Amdahl's law exists. Instead of guessing whether something will be faster, we can calculate it mathematically. By the end of this lesson, you will understand what parallel computing means, what speed up is, and how Amdahl's law works, and why adding more processors has limits. Before we dive into the math, let's ask a simple question. Why do we care about making programs faster? Think about the applications we use today. Video games, weather forecasting, artificial intelligence, scientific simulations, space exploration. These systems process huge amounts of data. For example, weather forecasting systems must process millions of calculations every second. Space agencies like NASA simulate rocket launches, planetary movement, and climate models using extremely powerful computers. If these calculations were done slowly, it could take days or even months to finish. So, engineers look for ways to speed up computation. What is speed up? Speed up is a way of measuring how much faster a program runs when we improve the hardware or parallelize the program. It compares the original running time to the new running time. Here is the formula. Speed up equals T sub 1 over T sub p, where T sub 1 is the time needed using one processor and T sub p is the time needed using multiple processors. Suppose a program takes 100 seconds on one processor, but only 25 seconds on 4 processors. The speed up would be speed up equals 100 divided by 25 equals 4. This means that the program runs 4 times faster. This is called linear speed up, which is the ideal situation. However, in real systems, we almost never achieved perfect speed up. Why? Because not every part of a program can run in parallel. Let's go back to the group project analogy. Imagine a project with two parts. First part, writing the introduction. Second part, writing the body of the report. The introduction can only be written by one person. This is called the serial portion. The body of the report can be written by many people at the same time. This is called the parallel portion. Even if we add 100 students, only one student can write the introduction. So, the introduction time never changes. This part becomes the bottleneck of the project. A bottleneck means the slowest part that limits overall performance. Computers experience the same problem. Even if we add many processors, some parts of a program must still run sequentially. This problem was studied by computer architect Gene Amdahl. In 1967, he introduced Amdahl's law, which predicts the maximum speed up possible when using parallel computing. The law tells us that the serial portion of a program limits the total performance improvement. Even with infinite processors, a program cannot become infinitely fast. The mathematical formula for Amdahl's law is speed up equals 1 over 1 minus p plus p over n, where p is the proportion of the program that can run in parallel. 1 minus p equals proportion that must run sequentially. N is the number of processors. This formula allows us to predict realistic performance improvements. Now, let's do a step-by-step calculation. Suppose a program is 90% parallel, 10% serial. That means P equals 0.9 and 1 minus P equals 0.1. Now assume we are using 4 processors. Substitute values into the formula. Speed up equals 1 over 0.1 plus 0.9 divided by 4. Compute the parallel portion. 0.9 over 4 is equal to 0.225. Add the serial portion. 0.1 plus 0.225 equals 0.325. Compute the final speed up. Speed up equals 1 over 0.325. Speed up is approximately 3.08. This means that with 4 processors, the program runs about 3 times faster, not 4. Now let's try something interesting. What if we increase the processors from 4 to 100? Will the program become 100 times faster? Let's calculate. Speed up equals 1 divided by 0.1 plus 0.9 divided by 100. 0.9 divided by 100 is equal to 0.0019. 0.1 plus 0.009 equals 0.109. The speed up is approximately 9.17. Even with 100 processors, the program is only about 9 times faster. That means 91 processors are not fully improving performance. This clearly shows the limitation of parallel computing. Now let's imagine something extreme. What if we had infinite processors? In that case, the parallel part would take almost 0 time. So the formula becomes speed up equals 1 divided by serial portion. Since the serial portion is 0.1, the maximum speed up becomes 1 over 0.1 equals 10. So no matter how many processors we add, the program cannot go faster than 10 times. This is called the maximum theoretical speed up. In our scenario, we assume that 90% of the program can run simultaneously across processors, while 10% must still run one step at a time. We then observed how the program behaves when using 4 processors, 100 processors, and an unlimited number of processors. Instead of focusing on calculations, we will now focus on interpreting the results and analyzing what the graph tells us about performance improvement. To understand the results, it is important to look at how the program is divided. In our case, most of the work, about 90%, can be distributed among processors and executed at the same time. This allows the system to perform several operations simultaneously, which improves overall performance. However, about 10% of the work must still be done sequentially, meaning it has to be completed step by step and cannot be divided among processors. Because of this, no matter how many processors we add, that part of the program will always take the same amount of time. When the program runs using 4 processors, we can already see a noticeable improvement in performance. Since most of the workload can be shared among the processors, the program finishes faster compared to using only one processor. However, the improvement is not perfectly proportional. Even though we are using 4 processors, the performance does not increase exactly 4 times. This happens because the portion of the program that must run sequentially still takes time to complete, and the processors cannot help speed up that part. When we increase the number of processors to 100, the program continues to run faster. However, the improvement becomes less dramatic compared to the earlier increase. At this point, the parallel portion of the program is already being processed very efficiently. Because of that, the sequential portion begins to dominate the total execution time. This means that even though more processors are available, they cannot significantly reduce the total running time anymore. If we imagine having an unlimited number of processors, the parallel portion of the program could theoretically be completed almost instantly. However, the sequential part would still remain unchanged because it must still be executed step by step. As a result, the total execution time cannot go below the time required to complete that remaining portion. This shows that the sequential work in the program ultimately sets the maximum possible performance improvement. Now let's look at the speed up graph. In this graph, the horizontal axis represents the number of processors, while the vertical axis represents the performance improvement. At the beginning, the graph rises sharply as we move from one processor to several processors. This shows that adding processors initially provides significant improvement. However, as the number of processors continues to increase, the graph gradually starts to flatten. This flattening occurs because the sequential portion of the program prevents further large improvements in speed. From the graph, we can see that performance improvement does not grow indefinitely. At first, adding processors provides large gains. Later, the improvement becomes smaller and smaller. Eventually, the graph approaches a maximum limit, which is determined by the portion of the program that cannot run simultaneously. This analysis highlights an important idea in parallel computing. Simply adding more processors does not always guarantee better performance. What matters more is how much of the program can actually run simultaneously. If a large part of the program still needs to run step by step, then increasing the number of processors will eventually stop making a meaningful difference. Because of this, improving system performance is not only about increasing hardware resources. Developers and system designers must also focus on reducing the sequential parts of programs and designing algorithms that allow more work to be performed simultaneously. By doing this, systems can take better advantage of multiple processors and achieve greater performance improvements. Based on the analysis of the speed-up graph, we observed that performance improvement eventually slows down even when more processors are added. This happens because a portion of the program must still run sequentially, which creates a natural limitation in how fast the entire system can execute. To address this limitation, several strategies can be applied. First, developers should focus on reducing the sequential portion of the program. Since this part cannot be executed simultaneously, it becomes the main bottleneck. By carefully analyzing the program structure, some sequential tasks can be redesigned or restructured so that they can be executed in parallel. Even a small reduction in sequential operations can significantly improve overall performance. Second, improving the design of algorithms is very important. Some algorithms require step-by-step execution, while others allow independent execution of tasks. Choosing or designing algorithms that support simultaneous processing allows better use of multiple processors. Another important strategy is breaking the workload into smaller independent tasks. When a large problem is divided properly, processors can work at the same time without waiting for each other. This increases efficiency and reduces idle processor time. Additionally, it is important to minimize delays caused by communication and coordination between processors. In parallel systems, processors often need to exchange data or synchronize before continuing their task. If this process is inefficient, it creates delays that behave like bottlenecks in the system. Optimizing communication helps maintain smooth and faster execution. So these concepts are not only theoretical, but are also applied in real-world systems used by large organizations such as NASA and Google. NASA handles extremely complex computations such as space mission simulations, climate modeling, and spacecraft trajectory analysis. These tasks require massive computing power and are processed using high-performance computing systems. To handle bottlenecks, NASA uses supercomputers with thousands of processors working in parallel. They carefully design their software so that Large problems are divided into smaller tasks that can be executed simultaneously. However, even with powerful systems, they still face limitations when certain parts of a program must be executed sequentially. Because of this, NASA continuously optimizes its programs to reduce dependencies and improve workload distribution across processors. On the other hand, Google processes enormous amounts of data every second, including search queries, video streaming, and artificial intelligence workloads. To handle this scale, Google uses large distributed computing systems where tasks are split and processed across thousands of machines in data centers worldwide. Google reduces bottlenecks by breaking large tasks into smaller units that can run in parallel and by distributing workloads efficiently across multiple servers. They also optimize communication between systems to avoid delays and ensure smooth performance even under heavy workloads. Ultimately, this demonstrates that improving performance in parallel computing is not just about adding more processors, but about designing systems that allow those processors to work together efficiently. Thank you.